Over 90% of power plants built in recent years around the world use green energy. Almost the entire capacity to generate new power across the globe is built around renewable energies.
In order to reduce the global greenhouse gas emissions, we need to do that in all sectors. It means also in energy generation, in power generation, and that works by building up renewable energy.
However, even if all the energy that was generated was renewable, there will still be sources of greenhouse gases in the future. Cement production, for example, it requires large quantities of limestone. The limestone is transported into long rotary kilns. At high temperatures, products such as calcium oxide are produced here, which are essential for cement production. This process emits large amounts of carbon dioxide. Waste incineration plants will also continue to emit greenhouse gases for a long time to come, regardless of climate-neutral electricity production.
Yeah, of course, we also have unavoidable greenhouse gas emissions, for example, in cement production or in municipal waste incineration, and we have to remove the CO2 from these point sources.
To achieve greenhouse gas neutrality, climate gases from unavoidable sources, such as cement plants or waste incineration plants, need to be captured on-site. This is done using carbon capture and storage technology, known as CCS for short. The CCS system is installed directly next to the plants and can remove, on-site, carbon dioxide from the gases emitted. The greenhouse gases that have been captured then flow through special pipelines to underground storage facilities. However, in addition to these so-called point sources, there will also be diffuse sources of greenhouse gases, such as agriculture. These climate gas emissions cannot be reduced using CCS technology. Aviation will also continue to be a problem. Assuming all aircraft eventually fly using climate-neutral fuels, they will nevertheless continue to emit nitrogen oxides, water vapor, and soot. These substances significantly exacerbate the greenhouse effects at high altitudes. Flying longer distances will always remain harmful to the climate. To achieve true climate neutrality, large quantities of carbon dioxide will also have to be removed directly from the atmosphere.
In order to reach greenhouse gas neutrality, we need to avoid greenhouse gas emissions first, then reduce those which we cannot avoid as far as possible, and finally compensate the rest by actively removing carbon dioxide from the atmosphere. And for removal of carbon dioxide from the atmosphere, we have different possibilities. First is nature-based solutions, however, for example, like afforestation. However, they are not completely safe that they would work, and they also depend on climate change. So for that reason, we definitely also need technical solutions for that.
Technical solutions already exist, like here in Iceland. This is a facility that sucks in the ambient air. In what are known as direct air capture, or DAC systems, the air flows through special filters. The filters adsorb the carbon dioxide. It is then removed from the filters and compressed underground. The problem is that the energy consumption for this process is extremely high at the moment. Scientists at the Institute for Microprocess Engineering at the Karlsruhe Institute of Technology want to solve this problem together with other institutes in the Helmholtz Association. The scientists are developing entirely new technologies for direct air capture systems. These systems will be especially efficient in removing CO2 from the atmosphere.
So even if we achieve all our goals regarding CO2 emission reduction by the year 2050, in order to reach greenhouse gas neutrality, we will have to remove a few gigatons of CO2. That is between, let's say, 1/10 and 1/4 of the current emissions. And for that, we need very efficient technologies.
To achieve this goal, scientists in Karlsruhe are developing new processes in their laboratories. They place special layers of electrochemically active plastics, among other materials, in a microreactor. What makes these thin films so special is that electrical energy changes their physical properties. The scientists are utilizing precisely this effect to their advantage.
With electrical energy, CO2 will directly react with the material in the reactor. When I reverse the voltage I apply, then CO2 will be again released, and it's very efficient.
Normal air flows into the reactor. The air molecules flow over one of the layers, which serves as a cathode. At the same time, electricity flows from an anode to this cathode. The flow of electricity causes the carbon dioxide molecules contained in the air to react with the surface of the cathode. The CO2 molecules accumulate here and can be removed from the airstream. When the cathode is saturated and no more carbon dioxide molecules can accumulate, airflow is stopped. If the current flow, however, is reversed, the CO2 molecules detach from the surface. This means the greenhouse gas concentrated in the cathode can be collected. Other energy-efficient direct air capture processes are also being developed at KIT. Scientists are investigating the structure of certain plastic bodies, for example. To remove carbon dioxide from the air, the scientists are incorporating the bodies into a separator.
So this is a carbon dioxide capture column. We use it for capturing carbon dioxide directly from air, and it is based on solvent absorption techniques. And the performance of carbon dioxide capture depends mainly on the contact area between the gas and the liquid.
In the reactor, a liquid flows over the plastic body. This forms an even film on the surface of the plastic body. At the same time, air also flows through the column. The carbon dioxide molecules contained in the air dissolve in the liquid. This liquid also contains certain amino acids. The CO2 molecules react with these amino acids. This enables the liquid to absorb the greenhouse gas. The liquid flows downwards out of the reactor. The concentrated carbon dioxide is then removed from the liquid using electrodialysis. In the search to find the perfect column, scientists are testing different structures. They use 3D printers to manufacture them.
And here we are currently working on the optimization of these structured packings for designing these kind of columns so that we can have maximum carbon dioxide capture efficiency.
On the roof of the institute, the scientists continue to test their system. It still works with the large filters that have been standard up to now, but it is less efficient than the systems in the laboratories. Nevertheless, there is one significant advantage.
The unit here is integrated into the ventilation system of the institute. That's the special point. So we take out the CO2 directly from the ventilation system, not from the outside air. And we do this because the concentration in the building is higher due to the people that work there. So ultimately, the efficiency is higher. We need less energy for the same amount of CO2.
The vision of the team of scientists in Karlsruhe could be summed up like this. In the future, new, efficient, direct air capture systems will use air in which carbon dioxide is already concentrated. CO2-enriched air is very common in cities. In offices, the carbon dioxide concentration can be up to 3 times higher than in the outside air. This office air is usually fed into air conditioning systems via ventilation systems. And this is where small direct air capture systems, such as those being developed by the Karlsruhe scientists, could remove the carbon dioxide. Once the CO2 is already concentrated in the ventilation systems, the efficiency of the entire system is further increased. Countless direct air capture systems could be integrated into a city's air conditioning system. There is one catch, however: the greenhouse gases then need to be stored safely.
No matter where I get the CO2 from, whether it's a cement factory or a building, I need an infrastructure for transport and finally storage of the CO2 underground. This needs to be developed and experimentally tested.
Scientists at the Karlsruhe Institute of Technology have also been considering ways to store greenhouse gases. They have examined special rock layers at different depths and in different regions of the Earth. The researchers are particularly interested in sandstone, for example. This mineral has extremely fine pores, which can then be used to store concentrated carbon dioxide. The rock is like a sponge, and there are pores in a sponge. It's the same here as well, except the pores are connected to each other. You pump the CO2 in and it sticks to the pores, and then the CO2 turns partly into water in the pores and part of it becomes mineral. And then the CO2 becomes rock again. This is happening at a depth of at least 800 or 1,000 meters, maybe even 2 kilometers. And we know from other deposits that such things remain underground for many millions of years, or even longer.
Oder noch viel länger dann auch im Untergrund verbleiben.
Scientists do not want to use just any rock layers for these storage sites, however. The carbon dioxide is injected into rocks enclosed in salt water. To reach these layers, the greenhouse gas is pressed deep down under the Earth's surface. At a depth of at least 800 meters and a pressure of over 70 bar, CO2 has very specific physical properties. It flows like a gas, yet at the same time it has the density of a liquid. It spreads under an impermeable cover layer. The CO2 now flows into the tiny pores of the rock, where it is retained by capillary forces. Over time, crystals will form from the CO2 and the ions in the salt water. These crystals are then joined to the rock. The carbon dioxide can no longer escape. However, the geologists at KIT are not only studying rocks that are suitable for CO2 storage, they are also considering how the captured carbon dioxide can be safely transported to underground storage facilities. There will have to be CO2 pipelines in Germany in order to be able to inject the CO2 underground. But there are already plenty of pipelines here, so adding another one would not be a problem. In the future, carbon dioxide will be captured at point sources such as waste incineration plants and cement factories, as well as in direct air capture plants. Then it can be transported via a pipeline network to underground storage facilities across Europe. But carbon dioxide that has been collected and concentrated can also take a different route. It does not necessarily have to end up underground.
The carbon dioxide captured from air or from a cement factory is also an interesting resource because you can make products out of that, carbon-containing products. This could be construction materials, this could be polymers, this could also be fuels for aviation, for example.
Building materials are one possibility for using CO2 concentrated by direct air capture. Every year, several million tons of so-called demolition concrete are generated in Germany. Parts of this material are reprocessed in recycling centers built for this purpose. Excavators transport the used concrete to a crusher. A magnet separates the reinforcing steel. What remains is an aggregate with cement residue still adhering to it. And this recycled aggregate can absorb carbon dioxide. First, the material flows into a special plant. It falls into different chambers via a conveyor belt. At the same time, concentrated carbon dioxide is injected into these chambers from below. The rock now reacts with the greenhouse gas CO2 in the large container. The calcium hydroxide contained in the cement residue reacts with the CO2 to form calcium carbonate. As a result, the recycled stones have a smoother surface, which simplifies processing them further. This rock can then be reused to produce concrete. As it contains more calcium carbonate, the compressive strength of this material is actually heightened. Additionally, the carbon dioxide is stored in it. Scientists at the Karlsruhe Institute of Technology are exploring technical processes so that the greenhouse gas can be stored in other products. They have their own energy lab, where they can produce what is known as a synthesis gas from carbon dioxide absorbed from the air in a special reactor. This synthesis gas can then be used to make high-quality products. Like plastics, for example. Since carbon dioxide was extracted from the atmosphere at the beginning of their production chain, the greenhouse gas is now stored in the plastic. E-kerosene, a synthetic aviation fuel, can also be produced, absorbing the greenhouse gas in the process. With fuels, however, there is the fundamental problem that the carbon dioxide is soon released back into the atmosphere. This means that the fuel is only CO2 neutral if direct air capture plants remove as much of the greenhouse gas from the atmosphere as would be released during a flight. In order for such complex technologies and processes to usher in genuine climate neutrality, they need a reliable legal framework. Until now, CO2 certificates have regulated the price of greenhouse gas emissions at the EU level and in other countries. Lawyers at the Helmholtz Center for Environmental Research are calling for clear international rules for the removal of greenhouse gases from the atmosphere. Industrial-scale CO2 capture is not yet regulated, and we need to develop a legal framework that ensures CO2 capture does not come at the expense of emission avoidance. Which means we can't sit back and say that we can pollute all we want now and someone will extract it later. We have to continue with renewable energies, but we must also continue to reduce emissions in industrial processes. And then we can extract what is unavoidable, what is left over.
Direct air capture should not be the alibi for continuing to use fossil energy sources. This would be too expensive, it would cost too much energy. It can only be used for compensating the residual emissions.
One thing is certain, carbon capture plants that remove greenhouse gases directly from streams of unavoidable exhaust gas are needed to achieve climate neutrality. In addition, efficient direct air capture plants will also need to remove carbon dioxide from the atmosphere. The greenhouse gas then has to be transported to underground storage facilities and stored there. Or it can be stored in products built to last. Without the development of these technologies, climate targets cannot be achieved. However, their installation will always involve considerable costs. It is essential to press ahead with the expansion of renewable energies, not only for ecological reasons, but also for economic ones. This is the only way to end the fossil fuel era and ultimately achieve true climate neutrality.